Okay, in this video we're going to be doing Calc AB Problem Set 22. There's a link to the problems and a playlist of all the problem sets in the description below. Let's get started. All right, given that f is the differentiable function with values in the table above. Okay, find the average rate of change, which is just algebra 1 slope, from 7 to 12. So that shouldn't be so bad. So we're going to just set up our slope formula, right? F of 12 minus f of 7 over 12 minus 7. F of 12 is 2. F of 7 is negative 5, so 2 minus negative 5. We're going to end up with 7 over 5, and that's part A. All right, part B, we want to approximate f prime of 6, show the setup. So f prime of 6 is approximately, using the approximately equal to sign. Don't use an equal sign there, you're going to lose a point. Approximately, you look at the table and you say, like, what values are to the left and the right of 6? Well, 5 and 7, so we're just going to find the slope between 5 and 7, basically the average rate of change on 5 to 7, and we'll say it's approximately the derivative. That's how you do it. I mean, you just kind of like have to accept that as a thing. Some people don't really like it, but there's really nothing else you can do. So here we get negative 5 minus 9 is negative 14 divided by 2, negative 7. All right, next up, we want to prove f of a is equal to 1. So we have f of x, and we're going to try to prove something about f of a. That's almost certainly intermediate value theorem. And as you do more problems, you want to kind of think about that. Like, as you read a problem, what strategy do you think is going to work on it? Here, we're on the same level as the given information. It's usually intermediate value theorem. So if I'm going to use intermediate value theorem, I need my function to be continuous. So I'm going to say f of x is differentiable, which was given. Therefore, f of x is continuous. You have to prove that you know that that implies, that differentiability implies continuity. But we do know that. All right, so we're trying to find f of a equals 1. So I need a place where we're below 1 and then above 1. I'm going to choose to use 7 to 12. You could also use 5 to 7. I mean, f of 5 is definitely bigger than 1. F of 7 is definitely less. I don't know. I wanted to go in order from left to right, so I'm doing 7 to 12. F of 7 is less than 1, which is less than f of 12. We already said continuous, so I can say, therefore, by IVT, f of a is equal to 1 for some a in between 5 and 12. Now, some people are like, but we didn't really do that. We showed it was between 7 and 12. I think most people can make the leap that 7 and 12 is between 5 and 12 as well. But if not, you could potentially say, you know, for some a between 7 and 12, therefore some a between 5 and 12. It's up to you. I mean, that's probably better or safer, I guess. Up to you. So the next one, we're given f and we want to prove something about f prime. Almost definitely going to use the mean value theorem. For using the mean value theorem, we need differentiable on the closed interval. Sorry, we need continuous closed, differentiable, open. Continuous closed, differentiable, open. Say that a million times. You heard me like say it wrong initially there. All right, prove f prime of c is equal to negative 7 for some c between 5 and 12. I mean, if you look at what we got as our answer in part B, we sort of already accidentally did this. So I'm just going to write my setup. F is differentiable, therefore continuous, which implies continuous. Therefore, by mean value theorem, f prime of c is equal to f of 7 minus f of 5 over 7 minus 5, which does equal negative 7. You do want to write that in, which equals negative 7 for some c between 5 and 7. Therefore, for some c between 5 and 12. So I did it there because I did think it looked a little cleaner. I don't know. You know, it's like you write one answer and then you decide, oh, I could have done better. You should always be thinking that. Hopefully you always think you could do better. All right, next question. Find dy dx for x squared y plus 2y squared minus x equals 5. Implicit differentiation. So we want to find the derivative with respect to x of both sides of this thing. So I'm just going to write that down. d dx of the left side equals d dx of the right side. And now we're just going to find the derivative. So the thing to remember here is that the derivative of y with respect to x is just dy dx. Remember that and you'll be fine. Also, basically every time you take the derivative of y, you need a dy dx by kind of the chain rule. So here goes. We got first, x squared, derivative of the second, dy dx, plus second, which is y, derivative of the first, which is 2x. I see people forget to use the product rule on these problems more than like any other rule. I'm not really sure why. But don't forget that, like x squared times y is definitely a product, requires a product rule. All right, derivative of 2y squared is really a chain rule problem, right? We got something squared. The derivative of something squared is 2 times that thing times the derivative of that thing. So we're going to get 2 times 2 is 4 times that thing, which is y, times the derivative of that thing, which is dy dx. Derivative of x is 1, derivative of 5 is 0. Number one mistake that I see, by far most popular, is forgetting the derivative of a constant is 0. People forget that all the time when they're doing these problems. Now we just need to solve for dy dx. So one thing you can do is like rearrange it so that everything with the dy dx, you just like factor out those coefficients. So I get x squared and then 4 plus 4y. Both of those had times dy dx. And then move everything that's not got a dy dx to the other side. So I added 1, I subtracted 2xy. Now I'm just going to divide by the coefficient of dy dx and have my answer. Dy dx is 1 minus 2xy all over x squared plus 4y. And that's it. I think the next one, the next problem is also implicit differentiation. So let's do it. We want to find dy dx for cosine of xy plus y equals 2. So when we find the derivative of cosine of xy, we're going to have to use the chain rule, right? The derivative of cosine of something is negative sine of that thing times the derivative of that thing. To find the derivative of xy, that's a product, so we need the product rule. So here goes. I'm going to write it out. I'm finding d dx of both sides. I sometimes skip that step. It's really a bad habit. You should do it. You should write this step out, but like, I don't know. It takes a while. It's a little annoying. All right, so the derivative of cosine we said was negative sine of the thing times the derivative of the thing. The derivative of xy requires the product rule. So at first, derivative of the second plus second, derivative of x is just 1. Now the derivative of y with respect to x is dy dx. And the derivative of 2 is 0. All right, so I don't know. You could do whatever you want on this. What I tend to do is just like in my mind, move everything that doesn't have a dy dx to the right-hand side and then divide by all the coefficients of dy dx. You might not like that. So here's what sort of a next step would be. I factored dy dx out of everything that has a dy dx. I basically distributed and kind of like collected like terms, I guess you might say. And then we're just going to solve. So add that y sine xy, divide by the coefficient, and we will get here. You'll see a lot of the time people rearrange that denominator so it says y minus x sine xy. Up to you if you want to do that. I mean, a multiple choice, you kind of have no choice. You have to like match it, obviously. But if you're just doing the work on paper, I think this is acceptable. All right, that's the end of this problem set. I hope this was helpful, and good luck.